So these are called three-dimensional dislocations. So now you already know from yesterday's exercise we did 2D dislocations. So 3D is the same idea, just instead of going to infinity in either direction, it has an end. So it's just a rectangle. And so this is we assume elasticity. So that means that this is this old definition in Latin, but it's basically like a spring, right? So the more force, the more displacement. And also this is a Poisson ratio. So it's like also our rubber band time, the beginning of our lecture. But the idea of Poisson ratio is that, if you pull something longitudinally, it gets thinner in the other direction. And so the Poisson ratio is the ratio of the axial extension to the transverse thinning. And so it's just an example of this behavior, as this person pulls and the rubber band gets thinner. This is an example of this Poisson effect. So when you specify something that's elastic, you have to say the Young's modulus, which is the relationship between the stress and the deformation, like the spring constant, and the Poisson ratio. And so this idealized elastic material has some stresses in 3 dimensions, and then the strains in 3 dimensions. And these lambda and the G are a combination of the Poisson ratio and these moduli, like the spring constant. So, and here's a simple, this is using the representation with Young's modulus, so the linear ratio of stress and strain, and then the Poisson ratio. So the thing is, it's 3-dimensional, and these elastic constants relate to each other. So now I'll just come to, so that's basically elasticity. So the 3D dislocations, the main program and the main source of this approach comes from Okada 1992. So it's this now famous paper from BSSA where he wrote down all these equations, very complex derivation, and also made available a Fortran program. But then many people rewrote all the equations in MATLAB, for example. But basically the idea is you have a rectangular source and you apply some displacement across it, and then you can compute what happens in the volume. And so the other thing that it does is it accounts for the free surface. So because, as I said before, in Andersonian faulting theory and in the case of dislocations, it matters that there's a free surface. So, and that's because, there's nothing up here, there's just air, and underneath there's the earth, the elastic material, and there can be no shear stress parallel to the surface, only normal stress. And this affects the displacement. So there's something called an image dislocation that corrects for the free surface. So I won't go too much into these details. This is the free surface here, there's the dislocation, and there's this image that kind of erases the effects of the dislocation that would be above the free surface. So then, can you imagine, this guy is this really good, is like you would call applied mathematician. So it's engineering, but he's keeping track of all these things, and he has all these pieces. So the equations are so big, he broke the equations into parts. And so these are all the parts of the equations that then you have to assemble in the program to make the calculation. So it's, on one hand, it's not so complicated. It's just very careful keeping track of everything. So the place where the Okada has been implemented most is in Coulomb, the software. So it says graphic, rich, deformation, and stress change software, but underneath is Okada. And so we'll come back to Coulomb in a minute. Here's the kind of thing it can do. So you have a fault, and you can compute the displacements in 3D. So we'll do this. kind of like we did yesterday. There are other pieces of software that do the same kind of calculation. This one's called Poly 3D. And the important thing about Poly 3D is instead of rectangles, it uses triangles. And so the nice thing about the triangles is you can have a continuous surface that changes in two directions. Like even a soccer ball, you can do, what's the effect of a pressurized chamber? Because if you have the rectangles, you have gaps, right? You can, like this thing, I can have two rectangles to do this, but if I have something up here, I'll have a gap. Whereas the triangles let us do completely closed surface. But it's not a big problem unless you're very close to the fault. The gaps don't matter. So that's why triangles or why the rectangles of Coulomb are okay. But if you look very close, you'll see these holes, and this can be a problem for complex faults. And so that's why these guys did Poly 3D. And so what the basic idea of these programs is you can have some remote stresses that you apply, and then you have your fault, and you put some slip on it, or you can put stress on it, and then calculate what the slip should be. And then you have some observation points where you compute displacement or stress or strain. And so these can be at a point, or the points can be on a grid, on a plane, and it can be horizontal or vertical or arbitrary, or it can be on another fault. So here's examples. This is a Poly 3D model for a normal fault with constant stress drop. So this would be the dip slip, what happens on that fault surface. So they use the Poly 3D a lot in seismic studies. So oil industry uses Poly 3D to look at 3D seismic volumes and interpret what they see. And so here are other slices. So the fault is red, but we have then these observation planes. It can be horizontal or vertical, arbitrary. So that's 5 minutes of dislocations 3D. So any questions on that? Okay, so then let's go to do Coulomb in particular. So the important point is static. So that means that there's no time in this thing. So if you remember, if you have an earthquake and it's rupturing, it has lots of stress around the rupture that goes with the seismic waves. And so we don't compute the dynamic stress changes with Coulomb. It assumes that the earthquake is complete and over, and then we just look at the total change in the volume. And this is generally okay, although dynamic stresses can be much higher than the static ones. So for some situations, you need dynamic stress transfer models, but we won't discuss that here. So this is the basic idea. We've already showed this a few times, this frictional behavior. So we have basically there's a balance between the shear force that's pulling on the brick and the resisting force on the bottom of the brick, that's its strength. And that's a function of the normal stress from the weight of the brick and the friction on the surface, right? So if you exceed it, then it can move. And this is like one-dimensional. If you have multiple faults or multiple bricks, then they can interact, which is important, right? So if you pull on the purple one, it has an earthquake. It transfers stress through the volume. So it's not a spring, it's elastic material, but it acts like a spring to put stress on the other piece of the volume, which could be a receiver fault. And so this language is important. We have source. So this is the one we control. And we say, okay, you move. What happens around you? And all the possible faults that can move are called receiver faults. So they receive the stress, and they may see if it moves. They can fail or not. And so the basic math of the Coulomb stress is that it's the change in stress, shear stress, plus the coefficient of friction. So if this is getting higher, that means that the shear stress is increasing, or the the normal stress, the strength is decreasing, so it's closer to failure. If it goes down or it's negative, that means that the shear stress went down, the driving stress went down, or the normal stress increased, and so then it's like clamped together. So that's simply what's calculated, but it has to be done in 3 dimensions on the fault surfaces. And so these guys, so these are the big names, are Stein, Lin, King, another one, Shinji Toda. He was at EPRI and Kyoto University and now is in Tohoku University. He's the lead author of Coulomb. And so you have some, basically the idea of some remote stresses. You have the failure planes. You have to take these remote stresses and resolve them into the shear and normal components of stress on the plane. And so you can use, this is basically the vector calculus that does it. And this is what's programmed. Like if we had a week, we could do this ourselves in MATLAB. It's a good lesson, but basically you take the remote stress and induced stress, you get the total stress, which is the stress tensor, and then the faults inside there. You have to take that stress tensor and compute the normal and shear on the single fault surface. So that's the normal stress here and the shear stress. And so then from these calculations, we can compute the change in the Coulomb failure function. And so how it looks then is we have our dislocation. So this would be the Okada fault, and he gives us the equations to calculate the stresses around it. And so you can just calculate an example calculation for faults parallel to the master fault. So these would be other faults with disorientation. And this is just the shear stress. So when we slip like this, actually in the area around it, we use up some of that shear stress. But off of the end of the fault, we increase the shear stress on fault planes parallel to the source fault. So the receiver fault is parallel. So then here would be the effect of the normal stress change, which is the friction times the change in normal stress. And so this can, be basically, unclamping here, and this is pushing it together more. And so when we add them together, so it's just added together across the whole grid, this is the Coulomb stress change for faults like this. So what this means is that where it's red, if you had a fault there that was the same orientation as the source fault, it would be moved closer to failure. And then the blue places, any faults over here would be moved further away from failure. So they're shut down. They're going to maybe take longer till the next earthquake. So there are many examples. So this, you see Toda. So they wrote many papers over, the last 20 years. And it's really like almost a brand name. You can see the colors and the style of presentations always looks the same. You say, oh, that must be Coulomb. And, but they've really done some great work to show how this, can be quite useful to explain successive earthquakes. So for example, there's this sequence where in 1986, so this is the San Andreas fault system, Southern California, San Andreas fault, San Jacinto fault. So this is Gayatri's fault from her master's here. There's the ocean. Los Angeles would be there. So this little earthquake, and this is calculating for basically other potential faults in the region, what the change in stress might be. So this little earthquake, it puts some red here and some red there. So those will be places we might look for the next earthquake. So a few years later, this Joshua Tree occurred. So it's actually Joshua Tree looks more in blue, right? So it occurred anyway. Right? But then, so that was how many years? That was 6 years later. And now what's important is this earthquake occurred. And look at what happens. So see, this stress right here is higher, and it's putting right onto this. So some people say it's like a fire, like a flamethrower. And so if the heat is on this fault here, and the same year, so like 2 months later, the Landers earthquake occurred, and it was right in that zone of increased stress from the Joshua Tree earthquake, which was a foreshock. So this is Landers, and then what's important, and this was one of the things where these guys started to get famous because it looked like it was kind of working. So you see this big red area. Well, the big aftershock was right there inside that increased Coulomb stress called the Big Bear aftershock. So in a way, you can use the idea that they argue was that Coulomb, even though it's kind of simple in terms of how it represents the Earth, it actually can be quite useful to anticipate these future earthquakes from the effects of prior ones. So any questions on that so far? You guys see this? So of course it works now. It doesn't always work, but this is an example where it worked quite nicely. So you see also this big red lobe here from Landers. There's some faults out here to the east. In 1999, they failed. Now, but parts were also, parts were in blue, so it doesn't perfectly work, right? Because, most of the Hector Mine fault was actually clamped. So it was moved further away from failure. But it happened, at least in, a little bit of it was in the red, and may have been the initiation where the hypocenter was in the area of increased stress. So sometimes it works, sometimes it doesn't quite so well. So here's just another view. This is a 3D view of the same thing and a little bit more of the terminology. So this is that same Landers earthquake with the aftershocks, the first 3 hours. And so the thing is, you can see that most of the aftershocks are in the red. And the blue is what we call stress shadow. So it's pulled the stress down. So it triggered this Big Bear earthquake. And then here is the first 7 years of earthquakes. And now here they show it better where the epicenter of the Hector Mine is right in the increased shear stress, or increased Coulomb stress, but it did, continue into these stress shadow areas. But one thing that they claimed was a really important positive outcome of their work was the very clear association with increased Coulomb stress and the aftershocks. See how almost all the aftershocks are in the red. So especially for the smaller earthquakes, they're very sensitive to this Coulomb stress increase, and they keep failing. So that's just one example of many. So you can do it also in cross-section view. So this is a surface rupturing thrust. So the surface rupturing thrusts tend to pull a lot of stress or Coulomb stress out of the upper crust. But you could see if you were going to have an additional slip, it would be deep down here. But this is already 15 kilometers. So this increased Coulomb stress would probably just increase the creep rate below the brittle part of the fault. However, and this shows the effect of that free surface, if we make it blind, we can get some higher stress above it. And so you might expect some additional cracking or small earthquakes shallowly above the main blind event. So then you add a few small earthquakes, and they basically consume some of that increased stress themselves. So this is enhanced stress, and then we put some new faults, and they absorb that stress and basically start to relax the stress around the initial fault. So then they did some other things. They showed that there was a few of these earthquakes that were on thrusts that were buried, and they tried to show that in general the aftershocks were in zones of increased Coulomb stress, and this increased Coulomb stress was kind of broadly distributed around the fault, so it explained why the aftershocks were all over the place. That's why it says diffuse. So this just some additional examples around a blind thrust fault that has a tapered slip. So Coulomb is quite a fancy program. So it can do constant slip across a single rectangle, or it can have many little rectangles and make more of this tapered slip, which is kind of like what we observe. We see contours of slip at depth. And this is changing aspect ratio. So that what this shows is really the location to have enhanced aftershocks or possibility of triggered bigger earthquakes is on the end of an existing fault. So if you break this fault, it's most likely going to want to cause failure on basically along that same fault for long strike. So let me keep going. So the last example, one of the most successful ones, is this earthquake sequence from Turkey from the 20th century. So maybe everybody knows about this on the North Anatolian fault. And it's a really great, amazing story. So what this shows is this is the map. The Black Sea, Istanbul is here. And this is the distance along the fault in kilometers. So it's 1,100 kilometers. And this is the cumulative slip. And so this distance is kind of in this arc. Okay? And so what they show is these earthquakes. So this was a big earthquake here. You see 6 or more meters and 300 kilometers. So how big was that earthquake now that we did all the scaling stuff this morning? 7.9 or something. It's like these other ones we did, only 300 kilometers and 6 meters of slip. So it's a little low of slip for the length still. So what you see is 1939, then 42, then 43. This is a little bit smaller. It's 200 kilometers, but only about 3 or 4 meters of slip. So this is like 7.5 probably. 1951, okay, there was 44, but then 57, 67, and then 1999. So it's not perfect, but it's like a bunch of dominoes, right? So you have dominoes, you line them up like this, and you push them, and they go, right? So same thing with this fault. It's like one earthquake after another along the fault. This really amazing earthquake sequence. And it happened, we think, in 1939 to 1992, like this, but it happened maybe, and this is, in this part of the world, it was kind of pretty good writing the whole time and good record keeping that was preserved. And so they have this sequence that maybe it went the other direction. So 1650, 1668, 1700, and then maybe before that it also went this way. So this fault has this kind of behavior of this sequential, a long strike failure, but big earthquakes. So here's a 3D view, and so what they did is they made a model of this where they tried to show they used Coulomb, and the nice thing about Coulomb is you can have many, many rectangles in your model. This gets more and more complicated. So they had, and if you remember now, you should start to recognize this from yesterday, from our 2D dislocations. Remember, we would have a deep fault. That was for the interseismic, and then we have a shallow one. So this would be the D depth right there. So what they did is they built this deep interseismic fault zone that's kind of the deep slip that's kind of constantly creeping, and it's loading, it's putting stress on these upper faults here. And they drive it at the slip rate from the geologically known slip rate from various places, so 24 millimeters a year, 24, some of these secondary faults less. And so you see that really, right, all those faults are are being loaded from below with high increase of Coulomb stress each decade. And so then they just show the sequence, how the increased Coulomb stress sequentially anticipates the next earthquake. So they take the 1939 earthquake and they show that, oh yeah, 1942 was right in the zone of increased Coulomb stress, right here. Then they add 1942, that earthquake, what they know, and its slip, to the model, and then they say, oh yeah, well look, 1943 was kind of right in the zone of increased stress. Same thing, 1944 was right there. 1957, 1967 is right in this zone of increased stress. 1967, and so on. And so this is really important because do you remember when the big earthquake was in Turkey? What year? (1999) was Izmit earthquake. And this paper, 1996. And so that earthquake was right there. So they kind of anticipated it, really clearly from beforehand. So that's what's really amazing about this study, because it's pretty good historically, but then the next earthquake was anticipated. So, so then they show a little bit final sort of thing, which is that you kind of have this combination. So this is time versus stress on the fault. So this secular stressing rate is just the background, that's me pulling, or it's plate tectonics. It's constantly loading. But this little earthquake trigger would be the effect from a nearby earthquake. It loads the fault. And if you say, well, this is the failure stress, then this earthquake trigger can bring that fault closer to failure. So it doesn't necessarily immediately cause the earthquake, but it has this, what they call a clock advance. And so then they even tried to get a little bit fancier, and they said, well, immediately we know there would be a kind of a really large increase because of the way that the friction works, and this is the kind of sort of the aftershock driven sort of behavior. So we would most likely expect the earthquakes to occur immediately, but no matter what, there's a permanent increase in time advance that persists always. And so they explored kind of what they tried to bring a little bit of time into the model at the end. So there are some different animations on this site. Maybe we can just look if there's one or two quickly, and then we'll play with Coulomb. So you can see this mostly coming from these guys, U.S. Geological Survey. This person, Rothstein, he's the one of the leaders, and you see they keep going. So this is even a study that looks at the effect from the Great Sumatran subduction earthquake on nearby faults, and sort of exploring, did the subsequent earthquakes occur where there was increased Coulomb stress. So they continue to do this work. Here's what I was looking for: teaching animations. So this may take a moment to load. Any questions so far? This is, let me just see. Yeah, let's look at this one, I think. So this is, assuming this works, this is 20 seconds. So this is the sequence I just talked about. Got stuck. I think my computer, when it's recording at the same time, it doesn't like to play other video. Oh, yes.
In this research, we must record every single earthquake a year.
Well, we mostly record the biggest earthquakes. Yeah, because they are the biggest sources of stress. So the source faults are the big ones, and they may influence the surrounding volume, and then so they can, a lot of times then they test looking at the small earthquakes around. So, but they just use earthquake catalogs from seismicity, from seismic networks to test, especially for the aftershocks. But usually the way to have to start is you have to say how these faults occurred. So they use the observed slip and the extent as something that's known, and they apply it to the program, and then they calculate the effect on the volume around. So that once you know 1939, then you can calculate what it did to the adjacent volume. But you could expect that small earthquakes might be promoted in these red areas as well. But 1939, there would be no good seismic network for small earthquakes. So, other questions? Are you guys ready to play with Coulomb? Enough lecturing? The movie? Let's see it. Try it one more time. Okay, so it just plays through. So, okay, so let's, if there's no questions. So, what I want to encourage you to do, so in this directory, there's really the book, basically a book. That's the user manual. Very nice. So I can't teach you everything just now. I'm just going to show a few things to help you get started. But if you like this, you should read the, experiment with the user manual, because it's well written, very complete. So I think if you guys agree, everyone find a computer with MATLAB and share maybe with somebody. 2 people can share, and we can do a few of these together, and then you can play. So one thing, just everyone listen to me for just a moment, is that I always teach computer classes, and what I've learned is that if you want me to slow down, or if you have a question, you raise your hand, okay? Then I'll come help you. But if you don't raise your hand, then I assume that you're going fine, okay? So rather than me asking all the time, everyone keeping up, I just look. If you want me to slow down, just stop. We can go slow, okay? So here we go. So go double click on Coulomb, and then you open the folder, and then you just double click on the Coulomb.m file. You can see this is some of the code. This is the main code. It calls other libraries. Okay, so everyone look up here at me for just a moment. So what you want to do, the main thing is function, let's see. So open existing input file. And then we want to go to input files. And then open this one. It's example2ll.inp. Can you see that? Example2ll.inp. Okay, ready? Okay, so what this is like this. And so, but this would be for Coulomb calculations, for looking for what are the most likely faults that will have earthquakes. So but it's only for that. For our calculations right now, we just only care about the geometry of the fault and the observation plane. And then you could experiment with changing the elastic properties, if it's maybe weak rock or harder rock. And then this is the grid, so minus 50 to 50, that's this thing here. C minus 50. And and it's calculating it every 4 kilometers.
The data is the focal mechanism and the regional set. Yeah.
Yeah, and if you know something about the fault, you know, like you from geology, maybe you know, okay, well we know it's down there. But if you wanted to look at, let's say this was a subduction zone earthquake, you could calculate, well, if it's, you know, let's look at what's the slip here. So this is 2 meters. So if there was 2 meters of slip on the fault, the surface displacement, well, here what you probably want to do is actually do vertical here. So you can see, okay, well, it looks like it's going to uplift about 10 centimeters only because it's blind. And it might subside at most 10 centimeters. So you could map, and if you knew where the shoreline was, you know, maybe you could say, oh, yeah, so the shoreline's going to lift up. Or if it's outward, maybe the shoreline will subside. That's kind of how I would be using it, is exploring ideas. You can't invert for locking depth with Coulomb very easily, but you can do forward models to find the best example. So what you would do is look at, you take a strike slip model, so like this one, and then you can change the parameters. So right now, the fault is from 5 to 15. So what we might say is make the fault go to the surface and save. So if I calculate the displacements vectors, this basically what the locking depth is doing is it's controlling how fast these vectors get, decrease in length. So just keep it in your mind, like see the length here. This is with a 15-kilometer locking depth. So watch what happens if I change this depth to 5. So grid parameters, if I change this just to 5 and rerun, so keep that in your mind, don't forget. There. So you can see it dies off, like they're kind of a little bit quicker if they got smaller. The other way, maybe the vectors are harder to see, you can do it with, if we just do, what's this one? No, that's not so helpful. But basically that's the way I would do it, is to just look at the profile perpendicular to the fault. And what we showed yesterday was that if you have the fault here and you have, you know, distance from the fault versus displacement, it goes up and it goes down like this, and the rate at which it goes back to 0 is controlled by locking depth. So the deeper it is, the wider the displacements are. So that would be how quickly the arrows become shorter. So I don't know if that's the best example, but that's how you could use this program. If I do like 25, really deep, so this should displace almost the whole map. Yeah. You can see some broader influence. See how these arrows are longer than they were before? If you look at 3D, this guy, you can see the fault is really... okay, so it's hard, let's see, hard to do 3D, maybe here. There. Okay, so this is, it's strike slip, so there's not much vertical. And actually this will be better at, you see right now the observation plane is at minus 7.5. So we don't see the die-off as easily as we do at the surface. So let me just do what I said again, but change this observation plane to 0. Calculation depth 0. So now if we rerun the 3D vector so we can see in 3D, see we're now at the surface. And so you see the verticals are greater. So this is the effect of the free surface. That's why you need a free surface. Like why Okada went through this effort to have the free surface part of the calculation. So now let's let me show my example again. So if I go to parameters we have right now, it's 25 kilometers deep, 3 meters left lateral. So we just do horizontal. So here you see, so now we go here, change parameters, input parameters. If I go to 10, let's just make it really dramatic difference. And functions, displacements, horizontal. So if I look 30, you see it's about half the size. So what that's showing is then that as I said, that the die-off and the displacements is more rapid as the locking depth decreases. And you can, the other thing we discussed was the deep one. So if you guys remember, that's the coseismic, the height of the fault. The other way is you can explore the deep interseismic. And so all we have to do there is we keep the calculation depth at 0, but we move the fault to, let's say, 10 at the top, and the bottom goes to 100. So now this will look like this. So this will be very smooth displacement field. But really, this would be better for this case if it was longer. So if we made the fault, so instead of, let's see, so that's minus 15. So let's see if I might crash it, but if I go minus 50 to, and minus, what's this? Minus 50 and minus 50. And then up the finish on this end is 50 and 50. Looks like it needs to be 50.2. Okay, let's see what happens. Might crash. Okay, so now the fault's very long, but it's very deep. So first, let's just look at the horizontal. Yeah. So here we see the edge effects, but if you're in the middle here, it's just you see these guys are going that way, these guys are going that way. And now if we look at this in 3D, displacements, 3D vectors. So it looks like the top of our fault is not quite updating. Remember we had this problem with the other one. It should be 10 to 100. Yeah, so let's save this. Save as. So just call it Ramon Inter for interseismic. Okay, so now I'll open that guy. Ramon Inter open. Now let's try it again. 3D vectors. Yeah. So there you can see, this is like the plate tectonic situation where what you would do is you would look at the surface displacements, and if I change the locking depth, one last example, and then I'll stop talking. I know maybe you guys want to play. So if we do 20, maybe 25. Now let's try 3 vectors. So I had it like this. It's hard for me to rotate. There. So here you can see the gradient is wider. That's because we pulled the locking depth down deeper, and that you can see there. A little, actually, see, it's still not updating the fault correctly, because see, it's still sitting at 10. So if you want to visualize, you'd have to go back here, save as, and then this will be Ramon Inter 2. Okay, input, open, Inter 2. 3D vectors there.